Section 3.5, Derivatives of Trigonometric Functions. In this section, we're going to derive the derivative rules for our 6 trigonometric functions: sine, cosine, tangent, secant, cosecant, and cotangent. Before we do, we're going to discuss the continuity of our 6 trig functions. It turns out all 6 trig functions are continuous on their domains. Below is a table of our 6 trig functions and their domains. Sine and cosine have a domain of all real numbers, so they are continuous everywhere. Tangent and secant are continuous as long as x is not equal to n pi over 2, where n is an odd integer. So tangent and secant are continuous everywhere except for odd multiples of pi over 2. Cosecant and cotangent have a domain of all real numbers except for integer multiples of pi. So cosecant and cotangent will be continuous everywhere except for integer multiples of pi. Because they are continuous on their domains, that means we can apply direct substitution to find their limits. One thing to note, though, is the trig functions have vertical asymptotes anywhere where the functions are discontinuous. And this is something you would have seen in pre-calculus while studying the graphs of tangent, secant, cosecant, and cotangent. Wherever they were undefined, there were vertical asymptotes. We'll see an example later on as to why they have vertical asymptotes where they are discontinuous. Another thing to note, in pre-calculus, we often switch between degrees and radians. In calculus, all angles are measured in radians. This is because all derivation of special limit properties and derivatives are done within the radian measure. So it's very important that our angles are measured in radians whenever we're applying trigonometric functions. Now we're going to evaluate each limit that involves a trigonometric function. We'll start with the limit as x approaches pi over 4 of cosine x sine x plus x tangent x. Since pi over 4 is in the domain of cosine, sine, and tangent, then cosine, sine, and tangent are continuous at pi over 4. X, being a polynomial, is also continuous at pi over 4. So this combination of sine, cosine, tangent, and x as a whole is also continuous at pi over 4. This allows us to evaluate the limit using direct substitution. So our limit will be equal to cosine pi over 4 sine pi over 4 plus pi over 4 times tangent pi over 4. From there, we can evaluate each trig function at pi over 4. Recall from pre-calculus that to evaluate trigonometric functions, we use the unit circle. If you need a refresher on how to evaluate trig functions, please check out the pre-calculus playlist to review the section on trigonometric functions. Using the unit circle, cosine pi over 4 is root 2 over 2, sine pi over 4 is also root 2 over 2, and tangent pi over 4 is 1. Root 2 over 2 times root 2 over 2 is 2 over 4, or 1/2. Pi over 4 times 1 is pi over 4. So our limit is 1/2 plus pi over 4. So just like with past functions we have worked with in Unit 1, since sine, cosine, tangent, secant, cosecant, and cotangent are all continuous on their domains, a viable strategy is to start by using direct substitution. Now we'll find the limit as x approaches 0 of tangent x over sine x. Just like before, we can try using direct substitution, which gives us tangent 0 over sine 0, but tangent 0 and sine 0 are both 0. So we have a 0 over 0 indeterminate form. What this tells us is we need to try to rewrite our function so that way when we try direct substitution again, we don't get 0 over 0. One of the common strategies we can use to rewrite this is rewriting tangent, secant, cosecant, and cotangent in terms of sine and cosine. Recall that tangent of x is sine of x over cosine of x. From there, we can proceed to simplify our function even farther. And after we simplify our function, we get the limit as x approaches 0 of 1 over cosine x. Try direct substitution again. We get 1 over cosine of 0, and cosine of 0 is 1, which means our limit is 1. Next, we're going to demonstrate why secant of x has a vertical asymptote at x equals pi over 2. A similar exercise can be done to verify that the trigonometric functions that are not continuous everywhere have vertical asymptotes where they're discontinuous. If we take a look at the limit as x approaches pi over 2 from the right, I can't use direct substitution here quite yet because secant is undefined at pi over 2. So what we can do is we can rewrite secant using the reciprocal property. So we'll rewrite the secant x as 1 over cosine x for both the right and the left-hand limit. Now, if we do try direct substitution, we do get 1 over 0 for both values. This is an indicator that our limits should be infinity or negative infinity. Therefore, we would have a vertical asymptote. Since they want us to evaluate the limit, we do need to figure out which infinity secant x would be approaching. To help us figure this out, we could use sample numbers, or we can just think about how cosine behaves on the unit circle. Keep in mind our numerator is positive 1. So as x approaches pi over 2, whether from the left or the right, our numerator is going to stay 1. The question is, what is cosine of x doing? Is it approaching 0 from a positive direction or a negative direction? To help us answer this, let's think about the sign of cosine based off of the unit circle. Pi over 2 is that top point on our unit circle. If we are approaching pi over 2 from the right, that means we are very, very close to pi over 2, but slightly larger than pi over 2. On the unit circle, angles close to pi over 2 that are a little bit larger than pi over 2 would be over in quadrant 2. If we recall from pre-calculus, cosine is negative in quadrant 2. So which infinity would 1 over cosine x approaches pi over 2 from the right? Since our numerator is positive while our denominator is negative, and positive divided by a negative is negative, our function will be approaching negative infinity. So secant x approaches negative infinity as x approaches pi over 2 from the right. As for x approaching pi over 2 from the left, when we approach pi over 2 from the left, we're dealing with values a little bit smaller than pi over 2. Well, angles that are a little bit smaller than pi over 2 would be in quadrant 1 on the unit circle. Cosine is positive in quadrant 1. Since a positive divided by a positive is positive, that means our function is approaching positive infinity. So as x approaches pi over 2 from the right, secant x will approach negative infinity, but it will approach positive infinity when x approaches pi over 2 from the left. One of the biggest problems with finding limits with trigonometric functions involved is that they don't interact too well with polynomial functions. For example, if we look at the limit as x approaches 0 of cosine x minus 1 over x, if we try direct substitution, we will get 0 over 0. But there's no way for me to cancel out that x in the denominator algebraically. To help us resolve this issue, we're going to look at a special limit that can help us when we're mixing trig and polynomial expressions. That is, the limit as x approaches 0 of sine x over x will always be equal to 1. The reason why this is true can be demonstrated on the graph that we have on the right, where observe that our graph of sine x over x is getting closer and closer to the point 0, 1. So as x is getting closer and closer to 0, sine x over x is getting closer and closer to 1. In order to use the special limit in the cosine x minus 1 over x problem, what we need to do is rewrite our expression to involve a sine x over x. The way we're going to rewrite this is by using conjugates, very similar to what we've seen in pre-calculus when we were trying to either simplify trigonometric expressions or verifying identities. The conjugate of cosine x minus 1 is cosine x plus 1. When we FOIL the numerator, we get cosine squared x minus 1. As for the denominator, because I do want to try to cancel out the x, or at least be able to have x interact with sine in some way to use my special limit, I'm going to keep my denominator factored. Since I want to rewrite my numerator from being in terms of cosine to being in terms of sine, I want to try to use the Pythagorean identity to help me out. Recall from pre-calculus that sine squared x plus cosine squared x equals 1. If we manipulate the Pythagorean identity a little bit, we get that negative sine squared x equals cosine squared x minus 1. So our numerator can be rewritten as negative sine squared x. Now I'm one step closer to using my special limit. I have sine x's on the top and a single x at the bottom. To help us better see our special limit within our problem, let's rewrite the sine squared x as sine x times sine x. Because I know that the limit as x approaches 0 of sine x over x equals 1, I'm going to put the sine x over x that I have circled in its own limit. And what's left over, I'll put in another limit. And this all works thanks to the product law for limits that we learned back in Unit 1. Our first limit to sine x over x, thanks to the theorem above, we know is 1. As for the other limit, we can attempt to use direct substitution again. Then evaluate. Sine 0 is 0, cosine of 0 is 1, negative 0 over 1 plus 1 will be 0, 0 times 1 will be 0. So the limit as x approaches 0 of cosine x minus 1 over x will be 0. Keep this limit in mind because we will use it later when we're trying to derive the derivative rules for sine and cosine. Next, we'll find the limit as x approaches 0 of sine 2x over x. One thing to keep in mind, we cannot pull 2 in or out of a trig function. However, we don't have to be so strict with the theorem above. Yes, it does state that the input has to specifically be x and the denominator has to be x. However, in reality, all we need is the input to the sine function and our denominator to both be the same and both approaching 0 in order for this limit to take effect. I can't do anything about the sine 2x, but I can multiply the numerator and denominator by 2. And then in the numerator, I can kick this 2 out of the limit. So I have 2 times the limit as x approaches 0 of sine 2x over 2x. Note that the input of sine and my denominator are both the same, and they do both approach 0 as x approaches 0. So that limit will also be 1, and 2 times 1 is 2. So the limit as x approaches 0 of sine 2x over x will be 2. Now we're going to start deriving the derivative rules for 6 trig functions. We're going to start off with sine x. We're going to come up with the rule for sine x using the limit definition. So using the definition we learned at the beginning of the unit, we have that f prime of x equals the limit as h approaches 0 of sine of x plus h minus sine x all over h. The problem is, how do we rewrite our numerator to try to cancel out the h? To help us expand the sine of x plus h, recall from pre-calculus, one of the family of identities we learned was the sum and difference identities. That is, sine of alpha plus beta equals sine of alpha cosine of beta plus cosine of alpha sine of beta. If we apply this identity to sine of x plus h, we obtain sine x cosine h plus cosine x sine h. What I find interesting now is I see a sine h while our denominator is h. Unfortunately, I only see sine h as a single term in the numerator. What we're going to do is decompose our fraction a bit. We're going to put the cosine x sine h in one fraction while putting the sine x cosine h minus sine x part of another fraction, both of which with a denominator of h. Notice that our two expressions are still equal. This is because when we add fractions, we keep the denominators the same and we just add straight across. Next, notice how in the second fraction, sine x is a common factor. Let's go ahead and factor out the sine x in the numerator in the second fraction. And our second fraction becomes sine x times cosine h minus 1 all over h. Now something interesting happens. We see the sine h over h that we saw in the theorem from the previous part of the video. But I also see cosine h minus 1 over h. This was the limit we evaluated as an example to demonstrate the usage of the sine h over h limit. If we use our limit properties, we can split the limit of this sum into the sum of the limits. Since cosine x and sine x do not depend on h, and our limit is being evaluated as h approaches 0, then the cosine x and sine x are considered constants and can be kicked out of the limit, thanks to the constant multiplier law. Now we can evaluate the two limits. The sine h over h from our theorem will approach 1. The cosine h minus 1 over h from our previous example will approach 0. Anything times 0 is 0, anything plus 0 is itself, anything times 1 is itself. And we're left with cosine x. So our derivative of sine x is cosine x. As an exercise, try finding the derivative of cosine x using the limit definition. The process is fairly similar, except you would want to look up what the sum difference properties for cosine are. Now we'll present the derivative of all 6 trig functions. In the previous example, we saw that the derivative of sine x was cosine x. If you use the limit process to find the derivative of cosine x, you'll find that the derivative of cosine x is negative sine x. As for tangent and cotangent, we can derive those using the quotient rule. Specifically for tangent, tangent of x is sine x over cosine x. So applying quotient rule, we get sine prime of x times cosine of x minus sine of x cosine prime of x all over cosine squared of x. The derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. If we clean up our numerator, it'll become cosine squared x plus sine squared x, which using the Pythagorean identity is 1. So our derivative of tangent x is 1 over cosine squared x, where if we use the reciprocal identity, we get that the derivative of tangent x is secant squared x. We can use the same strategy to find that the derivative of cotangent x is negative cosecant squared x. And I'll leave that as an exercise for you to try. As for cosecant and secant, the derivative of cosecant x is negative cosecant x cotangent x, while the derivative of secant x is secant x tangent x. These can also be verified using the quotient rule. Looking specifically at the cosecant x is 1 over sine x. Applying the quotient rule, the derivative of the top will be 0 times the bottom minus the top times the derivative of the bottom. The derivative of sine x is cosine x, all over the bottom squared. 0 times sine x is 0, so our derivative of cosecant x reduces to negative cosine x over sine squared x. Sine squared x is just sine x times sine x. So we can rewrite the negative cosine x over sine squared x as negative 1 over sine x times cosine x over sine x. 1 over sine x is cosecant x. Cosine x over sine x is cotangent x. So the derivative of cosecant x is negative cosecant x cotangent x. The derivative of secant x can be derived in a similar strategy. An interesting thing to note to remember which derivatives have negatives or not. Any trig function that starts with the letter c has a negative sign in its derivative, while all the other trig functions do not have the negative sign in their derivative. This can be helpful when trying to remember when to change signs or not. Next, we're going to find the equation of the tangent line to the curve of y equals sine x cosine x minus 3x at x equals pi over 4. Since we see the word tangent line, that indicates to us that we should take a derivative of our function. So let's start off by taking the derivative of y equals sine x cosine x minus 3x. Because of our derivative rules, we know we can take the derivative one term at a time. We'll start by taking the derivative of sine x cosine x. To find the derivative of sine x cosine x, we need to apply the product rule. In the product rule, it'll be the derivative of the first factor times the second plus the first factor times the derivative of the second minus, now we take the derivative of our second term, which is 3x. 3x is a straightforward derivative. Thanks to power rule, the derivative of 3x is 3. Now we'll continue to differentiate our sine x and cosine x, which is cosine x and negative sine x respectively. Since we're trying to find the equation of a tangent line, we know we need to find the slope of the tangent line, which means we do have to plug in the pi over 4. To make the computation easier, let's do a little bit of simplifying. For example, cosine x times cosine x is cosine squared x. Sine x times negative sine x is negative sine squared x. And we have the minus 3 outside. From here, it would be pretty straightforward to plug in the pi over 4. If you are really familiar with your trigonometric identities from pre-calculus, you could go a step farther simplifying and obtain that cosine squared x minus sine squared x was part of the double angle formula for cosine. In other words, cosine squared x minus sine squared x was cosine 2x. However, it doesn't matter whether you simplify it completely or not. Either version of these two derivatives will help you find the slope of our tangent line. Now that we have our derivative, to find our slope of our tangent line, we're going to take our pi over 4 and plug it into any version of our derivative. Doesn't matter which version you pick, you will get the same answer. Here, I am going to pick the most simplified version and plug it into the cosine of 2x minus 3 version. So our slope would be cosine of 2 times pi over 4 minus 3, which is cosine pi over 2 minus 3. Cosine pi over 2 is 0, so the slope of our tangent line is negative 3. The only problem that we have left with writing the equation of our tangent line is I don't fully know what point my tangent line is passing through. All I know is my tangent line intersects my curve at x equals pi over 4. To figure out the y component of the point that my tangent line should pass through, we're going to take pi over 4 and plug it into our original function. And we get that the y component of the point with an x coordinate pi over 4 will be sine pi over 4, cosine pi over 4, minus 3 times pi over 4. And if we work this out, we get that the y component is 1/2 minus 3 pi over 4. So our tangent line has to pass through the point pi over 4, 1/2 minus 3 pi over 4. Now that we have the point that our tangent line passes through, along with the slope of our tangent line, we can now write the equation of our tangent line. Starting off with the point-slope form, we get that our line is y minus the quantity 1/2 minus 3 pi over 4, which equals negative 3 times x minus pi over 4. From there, we can rewrite it into slope-intercept form, first by distributing in the negative 3. Then we can add the quantity of 1/2 minus 3 pi over 4, which gives us y equals negative 3x plus 1/2. So the equation of our tangent line in slope-intercept form is y equals negative 3x plus 1/2. Next, we're going to find the derivative of the following functions. First, 5x over tangent x minus 2 cosecant x. To take the derivative here, because the last operation we perform is division, we're going to set up the quotient rule. And by applying the quotient rule, we get that our derivative is equal to 5x prime times tangent x minus 2 cosecant x minus 5x times the derivative of tangent x minus 2 cosecant x all over tangent x minus 2 cosecant x squared. Now we can take the derivative of what's remaining in primes. The derivative of 5x is 5. As for the derivative of tangent x minus 2 cosecant x, we take the derivative one term at a time. The derivative of tangent x is secant squared x. The derivative of cosecant x is negative cosecant x cotangent x. Since we have a negative 2 in front of the cosecant x already, when we multiply the negative 2 with the negative 1 that comes from the rule, that would change the sign, giving us a positive 2. So the derivative of the negative 2 cosecant x is positive 2 cosecant x cotangent x. As for our denominator, we'll keep that factored since there is almost never a advantage gained by expanding the denominator in quotient rule. If we want to see if anything cancels out, we can distribute the 5 into its set of parentheses and the negative 5x into the other set, and we get that f prime of x equals 5 tangent x minus 10 cosecant x minus 5x secant squared x minus 10x cosecant x cotangent x all over tangent x minus 2 cosecant x squared. Unfortunately, nothing in the numerator collects or cancels or simplifies any farther. Now we're going to take the derivative of g of x, which equals 4x secant x all over x squared plus cotangent x plus 4. This derivative is a little bit more challenging than the previous one. We have to think very carefully about which rules to apply to find the derivative of this function. To determine which rule to use, remember we want to use the order of operations backwards. Whatever the last operation we would use to simplify, that is the first derivative rule we would apply. Here, our last operation we would perform as addition. So we would apply the sum and difference rule. The sum and difference rule tells us when we take the derivative of our function, we take the derivative one term at a time. Focusing on the 4x secant x over x squared plus cotangent x. In order to take the derivative of this, we have to think about what the last operation we would perform is if we were simplifying. The last operation we would perform is the division. That tells us we need to apply the quotient rule. And after setting up the quotient rule, we have the derivative of 4x times secant x times the quantity x squared plus cotangent x minus 4x secant x times the derivative of x squared plus cotangent x all over x squared plus cotangent x squared. As for the derivative of 4, since 4 is constant, its derivative is 0. Since anything plus 0 is itself, after this line, we will no longer write the plus 0. Now we'll focus on the derivatives inside of the quotient rule. For the 4 secant x, that is multiplication between the 4x and secant x. That tells us we have to use product rule to take the derivative of the 4x secant x. So I will set up product rule. And the derivative of 4x secant x would be 4x prime times secant x plus 4x times secant x prime. Notice that I'm putting my product rule in grouping symbols here. I'm picking square braces instead of parentheses. That is because that entire derivative must be multiplied by the x squared plus cotangent x. Now we'll turn our attention to the x squared plus cotangent x. Because the last operation we perform is addition, we'll take the derivative one term at a time. The derivative of x squared is 2x. The derivative of cotangent x is negative cosecant squared x. Now we just need to focus on the derivatives of the 4x and the secant x to finish up our derivative. The derivative of 4x is just 4, while the derivative of secant x is secant x tangent x. Copy the rest of what we have so far, and there's the derivative of our g of x. Note that this problem was a little bit more complicated because this is the first time we had to mix product rule with quotient rule. Keep in mind there is no set order which these rules have to be applied. You have to analyze each function carefully and determine each rule that you should apply based off the last operation you would perform when simplifying. As an exercise, you can try to simplify the numerator farther, but there really is not much we can do to simplify it from here. So we'll leave our answer like this.